section 4.7, and we're going to look at the three main types of chemical reactions for us in this course. So the bulk of this section is going to deal with precipitation reactions, and then we will do a pretty quick overview of acid and base reactions and then oxidation reduction reactions. But each of these is going to have their own section dedicated to them next. So acid base will be 4.8, oxidation reduction is going to be 4.9. We've already talked a good bit about precipitation reactions, but we will go into a little bit more detail, I guess, in this section. So with a precipitation reaction, we're going to have two solutions that have aqueous ions, and in mixing them, we are going to form some sort of insoluble substance. So essentially, the ions that are coming together from the two solutions, some combination of them is going to form an insoluble solid that will precipitate out. Okay, so the precipitate is going to be the thing that forms the solid. It is the thing that is insoluble, that if we were to have this solid and try to mix it in with water, it would not mix. Okay, so basically a combination of those ions are going to come together. They're going to like each other a bit more than each of them likes the water molecules themselves. So they will come together, form that solid, and then precipitate out. So essentially what we would see is maybe a cloudy mixture would form, or the solid would start settling at the bottom. But essentially we would get something that would look a bit different than just mixing the two solutions together. Okay, so in analyzing a precipitation reaction, we need to really know what the reactants are, so what we have in each of the two solutions. And in knowing that, we'll then be able to predict what the products would be. Okay, so what products are possible? We're going to need to keep in mind that positive is going to go with negative. All right, we would not form a solid that would be positive positive or negative negative. So the ions that come together out of necessity would have to be oppositely charged. Okay, so we would see a double replacement reaction where if we have AB as our one solution and then CD as the other one, we would form AD and CB. So either AD or CB would be our insoluble precipitate. So this whole year, we are striving to understand ideas and memorize things. So this is no different, okay? So knowing a little bit about the electronegativity differences is going to help us to, figure out what type of bonds we have and how attracted two ions would be to each other. But we are going to look at the trends for certain ions, and it will be necessary for you to know what the solubility of certain salts will be. So being able to predict in mixing two solutions together what the precipitate would be. Okay, so that table that I referred to you a few days ago, you are going to need to know these things. So for the purposes of the AP test, it is absolutely necessary that you know that all sodium, potassium, and ammonium salts, okay, these are going to be positive ions, Na+, K+, NH4+, as well as any nitrate salts, so NO3-, they are going to be soluble in water. So all of these salts would be soluble in water. Okay, but get to know these trends. Most chloride, bromide, and iodide salts are soluble. There are a few exceptions which will actually come into play whenever we, try out some of these when we try out some of these precipitation reactions. Okay, so like I said, get to know these trends. So we've seen this example before. So we've got potassium chromate, barium nitrate, and we know that when we put them together that, well, we are getting a yellow solid precipitate. So if we break this apart and get the complete ionic equation, all right, this is what we got: 2K plus CrO4 2 minus plus Ba2 plus 2 NO3 minus. These are all aqueous, by the way. Okay, and they're forming products. So one combination of these ions is going to give us this yellow solid. So the question is, what would that be? Okay, so trying to figure out what the products would be, it's really important to look at the charges. We know that the potassium and the barium would not come together because they're lightly charged. Same thing with the chromate and the nitrate. So what we would be forming would be potassium with a nitrate and barium with a chromate. One of those two combinations is going to be our solid. Okay, so we know that there is a reaction here because we are forming that solid. All right, so we know that one of these two is going to be that solid. So just looking at the trends from the last table, we would know that, well, all potassium and all nitrate salts are going to be soluble. So it is definitely not going to be potassium nitrate. Therefore, it must be the barium chromate. Okay, and there you go. So we have basically what we looked at before. So we have the separate solutions, but then we are going to put them together, and the barium and the chromate are going to come together and form that solid that yellow solid that would form and then settle to the bottom. So this is a nice little particular diagram like we've been practicing. And we know that, well, barium is an ion, chromate is an ion, so it's going to form a ionic solid. That's what this is right here. Okay, and then the potassium and the nitrate, they are ions here. They are still ions here. They are dissolved here. They are dissolved here. That means that they are staying in the same state, and they are going to be our spectator ions. Okay, so next we have silver nitrate and potassium chloride. So two solutions, and when they're mixed together, a white solid forms. So silver nitrate, potassium chloride, and we form a white solid. So which combination of these is going to be our solid? Okay, so we know that silver and potassium not going to come together. Nitrate chloride not going to come together. So it must be the silver trades the nitrate for the chloride. So is it going to be silver chloride, AgCl, or is it going to be the nitrate which trades the silver for the potassium? Would it be KNO3? Okay, and we know based off of what we said last time that it's definitely not going to be a potassium or a nitrate compound. So potassium nitrate is still very soluble. It must be our silver chloride. So on your own, I would like you to check out these ones and figure out which, if there's going to be a reaction. And if there is, then finish up the reaction, make sure that it is balanced. If there is no reaction because the new combination would still be soluble, then write that as no reaction. If there is a reaction, then write out the entire molecular formula like you saw here, right? So aqueous silver nitrate, aqueous potassium chloride yields are solid, the silver chloride and potassium nitrate. Okay, that's exactly what I want you to do here. And I will provide you with the answers later. All right, so we can apply stoichiometry to precipitation reactions. It's very similar to what we've done before. However, we would be starting with a solution, so we would have a certain volume and a molarity for that solution. Okay, so first we need to know what we've got. We need to make a balanced net ionic equation, figure out how many moles of each of the reactants we have to then figure out the limiting reactant, and then we can use that to figure out how many moles of the product we would be forming. Okay, then the molar mass to figure out how many grams we would be forming. So another practice problem for you, I'm actually going to let you do this on your own. So really the only difference here that we have now is that, okay, we are starting with a volume that has a molarity. So you're going to need to convert that into moles for each of these. But not only that, but remember, if you are writing out the net ionic equation, okay, recall that if the lead or with a nitrate is involved, that there are actually 2 moles of nitrate for every mole of lead nitrate, okay? Or like right here, there would be 2 moles of sodium for every 1 mole of sodium sulfate. So keep that in mind whenever you are working out this problem. Okay, so moving on to acid-base reactions, and we are going to define an acid-base reaction as one in which a proton or more than one proton is transferred between chemical species. So we're going to have an acid, we're going to have a base. We're going to have one that donates that proton and one that receives that proton. So think about what exactly is a proton and how are we going to represent that? Well, all a proton is, think about hydrogen. Hydrogen is a proton and electron, but when we remove an electron from our hydrogen, we get H+. So H+ is what we are going to use to represent a proton. Okay. So how are we going to define an acid and a base? That is pretty important here. An acid is going to be our substance that produces and releases H+ ions when they are dissolved in water. And a base is going to be something that produces hydroxide ions when dissolved in water. So this definition is what was given to us by Arrhenius. Okay, but for our sakes in this class, we are going to use the Bronsted-Lowry definition because that is really how we should define an acid and a base for our sakes for these reactions. So an acid is going to be the proton donor. So think of HCl, right? That's hydrochloric acid. It is a strong base. Is a strong acid, and it will release that hydrogen ion in solution, that proton. And then a proton acceptor would be like something that would release hydroxide ions because they would then accept that proton. So if we have OH minus plus H plus, that would give us water, okay? So a base is going to be the proton acceptor. It would take that H plus out of the solution. So something that we're going to talk about a lot more later is the concept of pH. So that is going to be the measurement of H plus ions in the water. So something that has a lower pH is going to have a lot more H plus ions. So that's why an acid has a low pH, because it donates a lot of H plus and will put that into the solution. Whereas a base is going to have a higher pH because they take the H plus out of the solution. All right, moving on. So we're going to look at redox reactions. And I have a couple of videos for you that I like to show. So just examples of redox reactions, which may not be something that you're super familiar with.
Like plants. Photosynthesis. Photosynthesis. Want to go to the park?
Okay, so photosynthesis, as SpongeBob said, is an example of a redox reaction. Like I said, I really like that because it's so dramatic. It's really overly dramatic. But rusting is another example of a redox reaction. Okay, so a redox reaction is going to be kind of similar to an acid-base reaction, if I'm going to be honest, but instead of transferring a proton, we're now transferring one or more electrons between chemical species. So this is not really something that can be easily seen because really what is happening is in this chemical reaction, the electrons are just going to be kind of shared a little bit differently. It's not like an electron is being plucked off of something and being sent to another thing, but in the formation of new covalent bonds, the amount of electrons that are being shared may be essentially slightly different. The electrons that would be assigned to a species. Okay, so we're going to use oxidation numbers to track the transfer of electrons, and I'll explain what those are a bit later. Okay, but a really good example of a redox reaction, just like photosynthesis and rusting, is going to be the process of combustion. So anytime a species reacts with oxygen gas at high temperatures, that is going to be combustion, and hydrocarbons like methane, like ethane, like ethanol, okay, those are all ones that easily combust with oxygen. They're highly flammable. And in that process, they will produce carbon dioxide and water if it is complete combustion. All right, so here we actually have the formation of sodium chloride going from the solid sodium to gaseous, solid sodium and gaseous chloride. Well, I should say chlorine, and putting them together, it's going to be a pretty crazy volatile reaction. And in the end, we get salt. Pretty cool. Okay, but this is an example of a redox reaction because there is actually a transfer of electrons in this reaction. Okay, so that is all that we're going to do for this section, and next time we will look at acid base in 4.8, and then we will look at redox like this much more closely in 4.9.